Hey guys, in this video I'm going to cover 6.5, which is logarithmic properties. This is going to be like everything we need to lead into solving exponential and logarithmic equations. So this section is dedicated to more of just the properties though. So just going off, going with the first property, we have log base b of 1. So let's just recall what a logarithm is asking us. Log base b of 1 means what power of b equals 1. So really it's asking us b to what power equals 1. It's asking us to figure out what's this value here. Well, we have an exponent property that says anything to the 0 power equals 1. Okay, so if you have a logarithm that's being evaluated at 1, the answer will always be 0, regardless of what the base is. So for example here, if we ask us to figure out what is log base 3 of 1, it doesn't matter what the base is. What's inside the parentheses is 1, therefore the logarithm will equal 0, because anything to the 0 power is 1. Now, the next property, log base b of b. So this is going with the same notation, same concept. This is saying what power of b will give me just b. Alright, and we know that b to the first power is b. So log base b of b equals 1. So this property just says it doesn't matter what the base is if what's inside the parentheses is the same. So if we have log base 25 of 25, that value will always equal 1. And then going just a little bit further from that one, let's say we've got log base b of b to the y power. So going with this same concept, this is actually called one of the inverse properties. This is an inverse property because this would be what power of b will give me b to the y power. And this uses the common base property, which says the bases would cancel, giving us that x equals y. So what power of b gives me b to the y power? Well, that power is y. Okay, and this is called the inverse property because if we have a logarithm with a base of b and we have an exponential with a base of b, the logarithm and the exponential cancels out, leaving you with just the power. And then the last one that we have here, or the last basic property that we have here, is another inverse property, which says if you have b being raised to a power of log base b of y. This is also an inverse one. If you have an exponential with a base b and a logarithmic base b power, these cancel, leaving you with just y. Now we don't see this property as often as we do the other ones, but that is also just another inverse property that I wanted to make sure I took time to go over. The next properties we have is what's called expansion / condensing properties. So sometimes when if you guys take calculus, it's beneficial to be able to take one logarithm and expand it out into several logarithms where each expression inside the logarithm is less complicated than the original. And so we use what's called expansion properties. And sometimes when we solve equations, we have multiple logarithms and we need to condense them back into one logarithm so we can take advantage of some inverse properties. So the first property here says log base b of m times n. That's a logarithm with a multiplication inside. This would expand to log base b of m plus log base b of n. So notice, we went from one logarithm to two logarithms. We had a multiplication between the two expressions. We now have an addition between the two logarithms. So we can do a quick proof of this. We want to bring in log base b of m and log base b of n into this. So we're going to say let x equal log base b of m, and y equals log base b of n. Then, the conversion of this, if x is equal to log base b of m, then that would mean that b to the x power equals n. And if y is equal to log base b of n, then b to the y power has to equal n. So now what we can do is we're ready to start the proof. So log base b of m times n equals, well, notice we can replace the m with b to the x. So log base b, b to the x. So we're going to substitute b to the x for m, and we're going to substitute b to the y for n. And then we have an exponent rule that says when you're multiplying common bases, we add the exponents. So that turns into log base b of b to the x plus y. And then now we can take advantage of this inverse property that says log base b of b to the y power, the log base b and the exponent base b cancel. Well, that's exactly what happens here. The log base b and the b cancel, leaving us with just x plus y. And then lastly, if we do our last substitution, what's x represent? Remember, we started off the problem by saying let x equal log base b of m, and we are going to let y equal log base b of n. And so we see that we arrived at exactly what our statement said. We have a logarithm of two things being multiplied, and through a series of equal equations and through a series of equalities, we have two logarithms split up through an addition now. We're not going to do the proof of all the properties, but that's one property. And we're going to, the proof of the rest of these is very similar to this one. So the next one, log base b of m over n. Well, that would expand to log base b of m. And let's think about this, guys. In exponent properties, when you're multiplying, you add the exponents. So multiplication inside of a logarithm turns into an addition. Go back to exponent properties. When we're multiplying bases, we add the exponents. When we're dividing bases, we would subtract the exponents. So log base b of m over n turns into log base b of m minus log base b of n. So this is just saying that if you have a logarithm of a division problem, we can expand that out into two logarithms where they're being subtracted. And then the last one says if we have log base b of m to the n power, then this just, if we have a logarithm of something to a power, this just says we have a logarithm, the power gets brought to the front of the logarithm. Okay, and I'll do a quick kind of just generic discussion of why that works. Log base b of m to the n power is equal to log base b of m times m times m times dot 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 times m, and this is a total of n times. That's what m to the n power means. And then this would split up into log base b of m plus log base b of m plus dot 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 plus log base b of n. Using this first rule that says if we have a logarithm of two things being multiplied, it expands into two additions. So if all these are being multiplied, then this is going to expand into a total of n additions. We have n additions. Okay, and so if we have n of those, let's say we had 5 of these, then we would say we have 5 log m's. Well, since there's n of these being added up, then this is equal to n log m's. Okay, and that gives us our generic kind of proof explanation of where this property comes from. Obviously, the proof will be a little bit more in depth, but jump in to do some examples of this. Alright, so for example, rewrite as multiple logarithms. Let's say we got log of x square root of x squared plus 1. Okay, so our properties are multiplication. Our properties are multiplication turns into addition, division turns into subtraction, and powers get brought to the front of the logarithms. Alright, so when we look inside this logarithm, we don't have any division, but we do have a multiplication. So this is going to break up into log of x, and then where the multiplication in turns into an addition, and then we're going to introduce a secondary log of the square root of x squared plus 1. Now, you'd be tempted to say that's the answer, but it actually goes a little bit further. This kind of goes back to a property we did a while back, and we did it in Algebra 2, that says when you have a square root, that's the same as raising it to the 1/2 power. So now we have log of x plus, and since we have a power, the power property says the power gets brought to the front of the logarithm. And then we get 1/2 log of x squared plus 1. Now you might say, well, what about the 2? Why does the 2 get brought to the front of the logarithm? The fact that the x squared and the plus 1, and the 1 has an addition in between it, means that has to be all treated together. And we don't have a property that allows us to take an addition and expand it. We only have properties for multiplication, division, and powers. So this is as far as this goes. Now let's say we've got natural log of x squared over x minus 1 to the third. So the fact that we have a division means we can rewrite this as natural log of x squared, and the division turns into minus natural log of x minus 1 to the third. And then once again, since we have a power attached to the x squared, we can bring that power to the front of the logarithm, and it becomes 2 natural log of x. And since this cube is attached to all of this x minus 1, it can also get brought to the front and becomes 3 natural log of x minus 1. Guys, this is one of those things that the more you do of these, the better you get, and then they just start clicking and making sense, and you can pretty much, once you get used to them, you can almost just go from the original problem to the final answer in one step. Alright, and then the last one of these we're going to do is log base 2 of 8 over x cubed x plus 1 to the 4th. So this would be log base 2 of 8, and then we have a division, so that's going to be a minus, but notice down here, we have a multiplication down here. And so we're dividing by multiple items. So what we're going to do is we're going to introduce a bracket, and then this can be log base 2 of x to the third, and then the multiplication turns into a plus, log base 2 of x plus 1 to the 4th. And then now we can kind of go through and do some cleaning up on this. So the first thing we might do is bring these powers to the front. So this is going to be 3 log base 2 of x plus 4 log base 2 of x plus 1. And guys, I'm not sure on the textbook, but I would imagine that when a problem like this happens, the textbook's either going to have the answer written like this, or the textbook's going to not include the bracket and it's going to distribute the negative. So since we're dividing by the x cubed and the x plus 1 to the fourth, the subtraction sign can be distributed to both. And you could have actually done that in the very first step, rather than introducing the brackets and then changing it to the subtraction distributed later on. Now, the last thing that happens on this one that doesn't on the other ones and is this right here, log base 2 of 8. And we'll come over here to the side. Log base 2 of 8. This means what power of 2 gives us 8? Well, the power is 3. 2 to the third equals 8. So log base 2 of 8 equals 3. So it's just kind of, it's very similar. So the fact that the fact that log base 2 of 8 equals 3 means that if a problem like these has this happen, the back of the book would go ahead, it's pretty standard to go ahead and just change that to what it equals. And that's probably the most common mistake people make, is they get down to the line above and they think that the line above is the answer, when actually it can be simplified further. It's very similar to like square roots. Like if we have square root of 7, well, square root of 7 is going to be an irrational number, so we would just leave it square root of 7. However, if we had square root of 9, we wouldn't write square root of 9 as our answer. We'd go ahead and simplify it down to 3. So since log base 2 of 8 is not an irrational number, it's a whole number, and the whole number ends up being 3, we go ahead and simplify it down to 3, and that's what we write it as. Alright, and we can also use these properties in reverse. So for example, we're going to do something where we rewrite them as a single logarithm. This is also called condensing, or to condense. Okay, so for example, if we have the natural log of 7 plus 3 natural log of 2. Since these are both natural logarithms, which means they're logarithms base e and they have the same base, we can rewrite these as a single logarithm. So this is going to be natural log of 7, and then the plus is going to return back to a multiplication. And we're not timesing by 3, we're timesing by 2. And since this 3 is in front of the logarithm, it returns to being a power. So we can rewrite this as natural log of 7 times 2 to the third, which then can be written as natural log of 56. And then we'll just do one more example of this, and then we'll get ready to wrap this video up. So let's say here, log base 5 of x plus log base 5 of 9 plus 2 log base 5 of x plus 1 minus log base 5 of 10. Okay, and you're just going to handle this one at a time. We're going to rewrite this as a single logarithm. So the key here, guys, is this is 4 logarithms, and they all have the same base. In order for these properties to apply, they have to have the same base. If one of them had a different base, you could not condense it with the rest of them, but you could condense the rest. We won't see that in this class, though. But for this problem, it would be log base 5 of x. The plus means we're going to be timesing by 9. The next plus means we're going to be timesing by x plus 1. But since the x plus 1 had a 2 in the beginning of it, that's going to go back to being a squared. The minus then goes to a division, and we're dividing by 10. And then just kind of rewriting this in standard form, instead of x times 9, we typically see this as 9x, x plus 1 squared, all over 10. Okay, and that's taking multiple logarithms and condensing it down into one. And this section is just about practicing this concept. And then when we get into the next section, where we start solving logarithmic equations, we'll actually see the use of these properties. So the last thing we want to cover in this video is what's called the change of base formula. Okay, so for example, if we want to know what power of 2 equals 7, well, that's not going to be a whole number. So what we can do is, that's going to be a decimal somewhere between 2 and 3, because we know that 2 squared is 4, and we know that 2 to the third is 8. So we know it's going to be somewhere between 2 and 3, closer to 3. But that's what we're trying to figure out. So, two ways we can do this. One is we can convert this to a logarithm. So this would be log base 2 of 7 equals x. And this goes back to our calculator at this point. But here's the dilemma. We've got the log button, which if you remember, log button means base 10. And we've got the ln button, which means base e. Okay. This is a logarithm with a base of 2. And we don't have a calculator command that allows us to type in a logarithm with any base. Some calculators have the ability, but most calculators do not. But what if I came over here and did this problem a little bit differently? Okay, we have this concept in algebra that we use repetitively that says whatever we do to one side, we can do to the other. As long as we do something to one side and we do it to the other, the equation remains true. So if we take the log of both sides, then what that allows us to do is that allows us to use the power rule and bring the x to the front of the logarithm. And then the reason we do this, the reason we take the log of both sides and then bring the x to the power to the front using the power rule is we no longer have an exponential, but now we have a multiplication problem. And so we can just very simply divide by log 2. Okay, and so notice here, we have x is equal to log base 2 of 7, and x is log 7 divided by log 2. So since x is equal to both of those, log base 2 of 7 has to equal log of 7 divided by log of 2. Now the kicker here is realizing that here the logarithm is a base 10. So we can't type log base 2 of 7 in the calculator, but we can type this expression in. So if we go to our calculator and type in log of 7 divided by log of 2, we get approximately 2.8074. Okay, and remember we said what power of 2 gives us 7? We said, well, it's going to be somewhere between 2 and 3. 2.8074 is between 2 and 3. And if I go in here and type in 2 caret 2.8074, we do see that we do get approximately 7. Now obviously since we rounded, we don't get exactly 7, but that's okay. We rounded to 4 decimals. So what the change of base property, notice here, the base is 10, what's inside the original logarithm is on top, and the base is on the bottom. Okay, so that's about the best way to remember that, is whatever the base is goes on the bottom. So for example, if we wanted to figure out what is log base 3 of 70, which means what power of 3 will give me 70 as an answer, we can then change this to log of 70 divided by log of 3. Okay, using the change of base formula. So if I type in log of 70 divided by log of 3, we get that it's approximately 3.8671. Okay, so, and then once again we can check that. 3.8671 should give us approximately 70, which it does. Okay, so now what's interesting about this is we could also change it to natural log. Natural log of 70 divided by natural log of 3. So if I go to my calculator and type in natural log of 70 divided by natural log of 3, notice what happens. We get the exact same answer. Okay, so in essence, guys, what the change of base formula actually says is log base A of m equals log base b of m divided by log base b of a. So this is just saying that we can take a logarithm with a base of a being evaluated m, and we can change it to a logarithm with any base that we want. It could be base 10, it could be base e, it could be any other base. We typically just deal with base 10 and base e because that allows us to use a calculator to finish evaluating the expression. So guys, That finishes up the video for 6.5. You have enough information to do all of the homework for section 6.5. Email me if you have any questions, guys. We only have 2 more sections, and that's 6.6 and 6.8. 6.6 is the exponential and logarithmic equations, and 6.8 is some application problems. I'll get those videos posted in the next day or two, and then we'll discuss the final exam for the class after those videos are posted. Guys, have a good